Hello everybody, my name is Muhammad Ali Amini. Today in this presentation we are going to discuss about the 5G NR spectrum. Please like and subscribe our YouTube channel if you like this presentation. Thank you so much. Let's start with the 5G NR spectrum. As you already know, the congestion in the lower operating bands combined with the requirement for wider channel bandwidth has led to inclusion of both low and high operating bands for 5G. That is 5G target spectrum allocation up to 100 GHz. The range of spectrum target by 5G is summarized in this picture. As you can see, lower frequency band, mid frequency band, and higher frequency band. The good RF propagation associated with the lower operating bands allows those bands to be used for the coverage solution. The relatively small channel bandwidths within those bands means that there is a requirement for 5G to focus upon improving spectral efficiency. The lower operating bands can be used for the all 5G use cases, which that is eMBB, URLLC, and MMTC. Also, the relatively small channel bandwidths limited the peak connection throughput achieved by eMBB application as well. The wide channel bandwidths available in the higher operating bands allows those bands to be used for high throughput capacity solutions. The relatively poor RF coverage and poor RF propagation within those bands means there is a requirement to focus upon improving the link budget. So 5G has been standardized to provide sufficient flexibility to address the challenges associated with both the low and high operating bands, like high-order MIMO and multi-user MIMO solutions can be used within a lower operating bands to help improve the spectrum efficiency, while beamforming can be used within higher operating bands to help improve the link budget. About these two concepts, about the massive MIMO and the MIMO concept, and also the beamforming, we will discuss in the next presentation as well. But here I'm going to explain some information about the lower bandwidth. As you know, we have the acceptable propagation, we have larger cell range, we have interference limited, we have bandwidth limited, as you are already aware of these issues. In lower band, also we are focused on improving spectrum efficiency by using high order MIMO and multi-user MIMO. And you will have the larger antenna element, and you will use the digital beamforming, and both FDD and FDD you can use in a lower operating and mid band. And then finally, about the small Doppler offset, which we'll explain in next page what's the meaning of a small Doppler offset plus low phase noise, which you need to use the small subcarrier spacing to control the small Doppler offsets and low phase noise. What about the higher operating bands? We can say we have limited propagations, we have small cell range, we have noise limited, larger bandwidth available, and also focus on improving the link budget by using beamforming concept. And your antenna element will be small, and you will use the analog and hybrid beamforming, and you will use just TDD for higher operating band. About the offset, you will have the larger Doppler offset, and also you will increase your phase noise. That's why you need to use the larger subcarrier spacing. What about the higher operating band? First of all, they have the limited RF propagation. Limited RF propagation leading to small cells and noise limited coverage conditions, interference limited coverage conditions are less likely at the high operating bands because intercell interference attenuated by RF propagation channel beamforming RF propagation channel. Also, we can say beamforming also helped to restrict intercell interference by allowing both directional transmission and directional reception. Small cell size. mean that delay spurred from the radio propagation channel are short. This allows the air interface waveform to use a short cyclic prefix. We can say this corresponds to a high subcarrier spacing. Wider channel bandwidth. Okay, in the higher operating band, increased potential for wider channel bandwidths. The higher operating bands are generally less congested and have greater quantity of spectrum than the lower operating band. Increase the frequency offset. Let's explain more about this frequency offset. See, increasing potential for frequency offset, which can reduce the signal to noise ratio at the receiver and thus degrade the bit error rate performance. Frequency offset leads to rotation of the modulation constellation. We can say this make the use of higher order modulation, such as 256 QAM, more challenging. In addition, when using an OFDM-based waveform and when frequency offsets are frequency selective, different offset experienced by different subcarrier, we can say, then subcarrier orthogonality is lost and there can be interference between subcarriers. Frequency offset require compensation within a receiver implementation to help reduce their impact. So the larger frequency offset in the higher operating bands provide an argument for using larger subcarrier spacing. And larger subcarrier spacing are less sensitive to frequency offsets. But how frequency offset can originate, it can be from Doppler frequency offset, which increase proportionally with the RF carrier frequency, like increasing the RF carrier frequency by a factor of 2, also increasing the Doppler frequency offset by a factor of 2. So the Doppler offset are dependent upon the relative of the transmitter and the receiver. They will increase for higher speed scenario as far we can see. Another is phase noise, which is generated by using non-ideal oscillator at both transmitter and receiver. That's why in this case we need to use the larger subcarrier in order to decrease the bit error rate. The higher subcarrier spacing associated with the higher operating bands lead to a shorter subframe duration and provide the potential for the lower latency. And the wider channel bandwidth associated with the higher operating bands leads to higher power consumptions by the digital to analog and analog to digital converters. In addition, power amplifier efficiency is likely to be lower with the higher operating bands. Any smaller antenna array element which provide increased potential for practical antenna arrays at both the base station and user equipment. These antenna arrays can be used to generate directional beams at both the transmit and receiver sides of the radio link. Both the base station and user equipment apply beamforming rather than just the base station. Here I'm going to show you about the coverage of each this operating band. First of all, this higher operating band, you can see the coverage will be around several meters, and you can use the massive MIMO. It will use for 5G NR radio. You will have dual connectivity concept, and throughput peak will be around 10 gigabit per second and more bandwidth available as we said. The second coverage point of view we can say about frequency range 1. We will explain more about what is frequency range 1 and 2 in the next slide. But here about the coverage concept, I'm show you in the mid band you will have around hundreds of meter coverage, which the MIMO it will start from 80R and it will use for 5G NR radio and also enhanced LTE. And the throughput peak data rate it will be around the 5 gigabit per second, and you will have the less bandwidth available, and the coverage it will be around 100 meters. And for the indoor coverage solution, more coverage you will have in the lower bandwidth, where it will be from the 450 till 900 megahertz, or from 1.4 to 2.6 gigahertz, which my move will be started from the 2T to R, and also anchor for 5G and enhanced LTE. And your throughput peak data rate will be around 100 megabit per second for the edge user, or 1 gigabit per second for central users. And it will be the less bandwidth available in the lower bandwidth, as you know. And your coverage will be around 100 of meters to even kilometers. But here, this is the complete of 5G network, which will be utilized low band, mid band, and the higher band. As you can see here about the baseline, and if your network as your operator, some operator has the 2G, 3G, 4G, and 5G network, they can finally, if they want to use fully utilized for 5G, it will be their roadmap. In this case, they will first started with deploying the 5G on mid-band by using the option 3 and non-standalone solution like dual connectivity. And in this case, they will increase the peak data rate, capacity, and lower latency. As you can see here, comparing with the baseline when you are not using the 5G and your network is just completing with the 4G network, you will have the better latency and capacity speed compared with the 4G network. But for cell edge performance, still you will have some issues. The second step will be adding the 5G coverage by using the lower bands in your 5G network. Okay, in this case, you will have the cell edge performance better than your baseline, even better than the 5G and mid band. So in this case, you will increase the cell edge performance, also your capacity, speed, and finally your latency. In the other options, it will be using your network and providing the 5G core. In this case, you will have the mobility on lower band, and also you will improve your control plane latency. In this case, you will have the good achievement and target. You will achieve the target of latency in the 5G network. And finally, if you utilize all the bands, means your 5G network, it's used the low band, mid band, and also the high band frequency range. You will have all these things together. You will improve your cell edge performance, you will improve your capacity and speeds, and also your latency. And that's why you will have the maximal coverage, capacity, and cell edge performance by utilizing all the bands, low, mid, and higher. And purely you will use the standalone option 2, for example, in this case. But about the duplex mode, now we are going to discuss about the duplex mode in the next presentation in the part 2. Thank you so much.